Hi. Now chapter 2, limits and continuity. In this chapter, we'll study rates of change, limit of a function, and continuity and asymptotes. The major subject is limit. In a nutshell, the limit is about checking the behavior of a function around a certain point. Now, let's begin with section 2.21, rates of change and tangent lines to curve. In the late 16th century, Galileo discovered the so-called Galileo's law of free fall. Once an object is dropped and allowed to fall freely, then the fallen distance is proportional to the square of the time. So such motion is called a free fall, and the formula is given in this way. The distance fallen is the same as 16t squared in foot. Okay. Now, for that equation, let's try to measure average speed. The average speed of the rock will be computed in this way. If we choose the interval from t0 to t1, then now that is ft1 minus ft0. That means the change in the distance during the time and the time elapsed. So that we say distance traveled divided by time elapsed. So that is average speed. Okay, let's try to solve this example. A rock breaks loose from the top of the tall cliff, and we have to measure the average speed during the first 2 seconds of the fall. Okay, for part A, okay, that means that in the problem it is asking that we want to find the average speed during first 2 seconds, so that t is moving from 0 to 2. So the average speed, okay, average speed must be here f of 2 minus f of 0 divided by, now that is 2 minus 0. Okay, what is f of t? Here we are using the Galileo's the free fall, the formula, that is f of t equal 16t squared, right? So that f of 2 is now 16 times 2 squared minus f of 0 is 16 times 0 squared over 2. Okay, second term in the numerator is 0, and the first one is now 16 times 2 squared over 2. So that 2 will be cancelled, so that is a 32. Okay, of course this one is now the feet per second. Okay, now let's go to the part B. And during the 1 second interval between t equal 1 and t equal 2, okay, that means that we have to find average speed for t is between now 1 and 2. So that the average speed must be here f of 2 minus f of 1 divided by the time elapsed is 2 minus 1. Okay, what is f of 2? Again, same as earlier, that one. So that 16 times 2 squared minus f of 1 is 16 times 1 squared and divided by 1. Okay, so that is 64 minus 16, which is the same as now 48. Of course, the same unit, foot per second. Okay, now we try to find the speed. The speed means instantaneous speed. And at t equal 1 and t equal 2, but we don't know yet how to find the instantaneous speed, so that we'll try to measure the average speed, so which is change in y, the distance traveled, divided by the time elapsed. And by using the Galileo's law of free fall, we can get such a quotient. And if h is small and becomes smaller and smaller, then we may see some tendency, and also we may see some approaching limit. Then we may try to use that as the speed. So here, that is by using this formula, and we try to choose h here smaller, so that we can get the value. And here, that can be gotten by using implementation. Okay, here we have octave window, and octave is a free alternative to MathTalent. So you can implement one code and you can run on MathTalent and octave. They are not exactly 100% the same, but in the beginning level, we can say they are the same. Okay. Now in this directory, I saved here so-called freefall.m. You can run it on the MathTalent and on, like this one, octave. Okay. Now the f of t is defined 16t squared, and the quotient is defined now along with two variables, and f at t0 plus h minus f at t0 divided by h. So here, I is moving from 0 to 4, and h is defined to be 1 over 10 to the I, and q1 is quotient at 1, and q2 is quotient at 2 for the given h. So it's a printout. So you can run it by clicking that button, which is the same as now an F5, the function tree 5, so that I'll hit F5. Okay, so it's executed, and if you go here, command window, then you can see the result, free fall is executed, and the result came out. So as you can see over there, the result in this lecture note is exactly the same as that computation. In fact, it's copied from that, the execution. Okay. In this way, by using computer, you can check it. Anyway, here the result is now average speed as h, the interval, the decreases. Now the value at 1 is converting to 32. Looks like 32 something is converting to 32. At time is 2 is approaching to 64. So this result suggests that the rock is falling at a speed of 32 feet per second at t equal 1 and 64 at t equal 2. Okay. Now let's conform this result to algebraically. Now change in y divided by change in t at t equal 1 can be written in this way. So that is f of 1 plus h. This term, the first term in numerator is the same as f at 1 plus h. The second term is at f, okay, at 1. Then by expanding, we can get this one and eliminate this 16 and that 16. So that remaining part is, after multiplication, 32h plus 16h squared on the numerator, and divided by h, we can reach at that one. Apparently, if h equals 0, then it is approaching to 32. H can be negative, positive, it doesn't matter. Anyway, this term will approach to 0, so that now the limit must be 32. Exactly same way for t equal 2, we can check the quotient. Now, the first term on the numerator is the same as f2 plus h, and the second term is same as now f of 2. And again, same way, algebraically, you can simplify in this way. That is 64 plus 16h. So here again, apparently, h equals 0, it is approaching to 64. That is exactly we already observed from the computation. Okay, with that experience, now we can officially define in this way average for general function. So earlier we tried to get for the distance, foreign distance, we tried to get average speed. Now for general function, function of x, we try to define average rate of change, and with respect to the independent variable x, and over the interval x1 and x2, which is now change in y divided by change in x. Change in y is now f at x2 minus f at x1, and change in x is same as x2 minus x1. If we here write x2 is same as x1 plus h, then now it can be written in this way. That is exactly the formula we used to when we are dealing with Galileo's law of free fall. So that is for general function, general independent variable, the general function f, we define the average rate of change. Okay, geometrically, this definition can be explained. Here, that is x1 and x2. Change in x is now delta x, which is x. Change in y is change in height. So f of x2 minus f of x1. So that is exactly now this delta y over delta x, which means that there is the slope of this line is exactly the average rate of change. And this line passing these 2 points is called secant line. So that now, the average rate of change of f over the interval is the same as the slope of the secant line. Okay, now we try to define tangent line. We already know that once h goes to 0, and also there is some converging limit, then we try to use it as the instantaneous slope, and instantaneous the speed in Galileo's law of free fall. So we'll use that for defining tangent line. Okay. Now here, if you are choosing h positive for the given function, then the secant line will be made that way. As h equals 0, now secant line will move in this way, and then once it is approaching to some line, and also if you do this one from left hand side, which is related with h is negative, so that the secant line is converting to some line. And once left approach and right approach, the limiting line is the same, then we say that is tangent line. For some cases, the limit doesn't exist. For example, function shape is now go up and has cursor and go down like that. Then left hand side, the limit will be here approaching to that direction, and right hand side, the limit of secant lines will be that way, so that they are not the same. In this case, there's no tangent line. But once it's smooth like that, the curve is smooth, then, and you can easily see from right hand side, from left hand side, the limit of secant lines will be the same. In this case, we define the tangent line here now officially, but it's a sort of rough definition. And the tangent line to the curve at P is the limit of the secant lines as now the point as h goes to 0 converges to P from either side. From both sides, the limit must be same. Then we can say that is tangent line. Okay, now let's try to find the slope of the tangent line to the parabola y equal x squared at 2 and 4. Okay, let's try to make a picture. So it's x-axis, that is y-axis, and y equal x squared is given in this way. Okay, there is a touching here. And that is y equal x squared. Once x equal 2, then y equal 4. Okay. For at the point we want to find the tangent line. That's the problem is asking. So and so far we try to get tangent line as a limit of the secant line, so that of course over there, and the slope of secant line is average rate of change, and that limit once exists, then that is of course the slope of tangent line. So we'll follow the mathematics we developed. Okay, here, so that we start with the average rate of change, that is f, and 2 plus h, and x is 2, and h distance minus, and f at 2 divided by h. That is now average change of rate. Okay, that is f of x is now x squared. So yeah, this is in the numerator. Yeah, 2 plus h squared minus 2 squared divided by h. So it is the same as, after expanding, we can get 4 plus 4h plus h squared minus 4 divided by h. This minus 4 plus 4 cancel out, and after dividing by h, we can reach this 4 plus h. And either side, h is less than 0 or larger than 0. That means q is approaching from left hand side or right hand side. Anyway, as h goes to 0, we can see that is approaching to 4. So we can say that the slope of the tangent line must be 4. And also second part is asking you to write an equation for the tangent line. So already we know that here the slope is 4 and the point P is now at x equal 2, y equal 4. So that by using slope point formula, we can get here y minus 4 equal m, which is now 4, and x minus x0, that is 2. So that is exactly an equation of the tangent line. Okay. Okay, we have a remark and from above examples, and now you can see that the average rate of change converges to a certain number. If it is happening as h goes to 0, then the number can be viewed as the instantaneous rate of change. Of course, that is the same as the slope of the tangent line. Okay, that's the end of the section. Let's go to one problem in the section. Now f of x is defined as x squared minus x. Then by using the method in equations 2.4 and 2.5, that is basically here algebraic confirmation here. So start with average rate of change and try to find the limiting behavior as h goes to 0. By using the technique, we want to get the 4 at these 4 points. We try to get instantaneously slopes, and then after finding the 4, and you can now find a function representing that 4 points. So let's say we'll do one of them. Okay, for part A, okay, we choose x equal 2, but we have to do for this all 4 points, but here we'll do only at 1 point. Okay, then exactly the same way as in the examples, here we have to measure f now 2 plus h minus f2 divided by h. Okay, that is same as f2 plus h. Okay, that is, now we have two terms, so that 2 plus h squared minus 2 plus h, that is f2 plus h, minus now f2, then that is now 4 minus 2, which is now 2. Okay, let's write down here 4 minus 2. Okay, now divide by h. Okay, so we'll expand, and for that one, there is a 4 plus 4h plus h squared, and minus 2 minus h, and that is now minus 2 divided by h. So that is now the constant for minus 2 will disappear, and along with the 4h and minus h, there 3h divided by h, which is 3. Now divided by h, which makes h, so that we know that that is converging to 3 as h goes to 0. So in this way, you can find for each of these 4 points and the number, that is a slope of the tangent line at the point. Right now this is at x equal 2, but you can find for each of these points these numbers and try to make here now the plot, so that right now for the this result, okay, that is here slope, and that is x direction, and here x equal 2, Now the slope is 3. Okay. In this way, you can get the result, and if you put a 4 point here, then you'll see the pattern, and then try to express the pattern in an equation. Then that's the answer for part B. Okay, this is the end of the section 2.1. Thank you.